The unit circle. A unit circle is a circle with radius 1. Here we have a unit circle centered at the origin. So I have centered at 0, 0, a radius of 1. So the quadrantal angles pass through 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Now let's review our special right triangles, but on a circle with radius 1. So first, let's recall our 30, 60, 90 right triangle. So on our 30, 60, 90 right triangle, if you'll remember, across the 30-degree angle was a side length of 1. Across from the 60-degree angle was a side length of square root of 3. And the hypotenuse was 2. If I want to think about a unit circle where the radius is 1, which corresponds to the hypotenuse, then that means that I'm shrinking down the original ratios of my 30, 60, 90 triangle by dividing them by 2. So 2 divided by 2 gave me 1, and then if I divide 1 and square root of 3 by 2, that gives me my other two side lengths, my opposite and my adjacent. And I can do something similar to the 45, 45, 90 triangle, which you recall is here with side lengths 1 and hypotenuse square root of 2. If I want the hypotenuse to be 1, I'll need to divide all of my side lengths by the square root of 2, right? Scale it down. So square root of 2 divided by square root of 2 is 1, and then the side lengths, 1 over square root of 2, rationalized to be radical 2 over 2. And the 30, 60, 90 triangle, again, is what we would use to find those side lengths for the 60-degree angle, just thinking about it in a slightly different way. Now we're going to redefine the 6 trigonometric functions for the real number t. So let t be a real number and x, y a point on the unit circle that corresponds to t. So here's a picture of a unit circle, a circle with radius of 1. This one's centered at the origin. And what we want to do is think about t, this real number, as a length of an arc that corresponds to a specific point x, y. Then we're going to define sine of t. Again, t is that real number, corresponds to the arc length. Sine of t is equal to the y value of the coordinate point that that arc length ends at. Cosine of t is the x value of the coordinate point. Tangent of t is y over x. And we have the familiar reciprocal functions for cosecant t, secant t, and cotangent t. Here what we are doing is, instead of thinking about the input of the trigonometric functions as angles, we are extending to think about instead the input being simply a real number. Here's just another visualization to help understand what we're talking about. So we're on the unit circle, the radius is 1, and the input is a real number t. Again, t is an arc length. And so we are defining sine of t and cosine of t as the values of the coordinate point that corresponds to that arc length. So cosine of t is the x value, that distance, and sine of t is the y value, this vertical distance here. So the difference is, again, that we're thinking about t as a real number, as an arc length, as opposed to thinking about the input of a trig function as an angle. But you'll see here that t is also labeled as this interior angle, because it turns out that the measure of this angle is equivalent to the measure of this arc length. So let's take a look at why. Since the radius of the circle is 1, t is actually equal to theta, that interior angle, in radians. So it comes down to remembering the formula for arc length. So the arc length, s, was equal to the central angle times the radius. Well, if the radius is 1, then the arc length, in this case we're calling it t, is equal to the angle theta times 1. So t is just equal to theta. So then we get our familiar sine of theta is equal to y. Cosine of theta is equal to x. Tangent of theta is equal to y over x, right? But x cannot be 0 because we can't divide by 0. And again, the familiar reciprocal functions. So now this new way of thinking about defining trigonometric functions really just allows us to think about inputting real numbers rather than thinking about inputting strictly angles. Now let's talk about the unit circle. When you hear the phrase the unit circle, this is what's typically being referred to, which is a unit circle, a circle of radius 1, but with very specific angles indicated and the corresponding coordinate points. So we have our 30, 45, and 60 degree angles, of course in radians, pi over 6, pi over 4, and pi over 3, with the corresponding x and y coordinate point. So we have radical 3 over 2, 1/2, being the x and the y value, radical 2 over 2, radical 2 over 2, being the x and y value at 45 degrees, and at 60 degrees we have 1/2 radical 3 over 2. And then of course we also have the quadrantal angles and those coordinate points, the combination of 1 zeros and negative ones. And in the remaining quadrants we have angles that are related to these 30, 45, 60 degree angles in that those are the reference angles to these other angles. So in quadrant 2, for example, 150 degrees has a reference angle of 30 degrees, and 135 degrees has a reference angle of 45, and 120 degrees has a reference angle of 60. So these other angles in quadrants 2, 3, and 4 are still related to the angles in quadrant 1 that come from those special right triangles. The only difference is that the signs are going to vary based on which quadrant I'm in. So in quadrant 2, the x values are negative and the y values are positive because they're going to the left and up. In quadrant 3, the x and y values are both negative because they go left and down. And in quadrant 4, the x values are positive because I go right, and the y values are negative because I go down. So there's a lot of symmetry happening in the unit circle. And over here, this is just a zoomed in image of quadrant 1 of the unit circle, just because it's so important. It really is like the foundation for finding the remaining values in the other 3 quadrants. And here you can just really see how these coordinate points are coming from those special right triangles that we can see are embedded in this unit circle here, where the radius is 1 for each of those, so that corresponds to the hypotenuse of each of those triangles. Find the exact values of the 6 trigonometric functions given theta equals 5 pi over 6. So here we'll go ahead and assume that we're given the unit circle here and just make sure that we know how to use it. So the angle is 5 pi over 6, which is going to be right here in quadrant 2. And we're looking for the exact values of all 6 trigonometric functions. So we have sine of 5 pi over 6 is going to be the y value of that coordinate point. So the y value is 1/2. Cosine of 5 pi over 6 is going to be the x value of that coordinate point, which is negative radical 3 over 2. And from here, tangent of 5 pi over 6 is the y value over the x value. So we have 1/2 over negative radical 3 over 2. So we can think about multiplying by the reciprocal times negative 2 over radical 3. So the 2's are going to cancel. I get negative 1 over rad 3. And rationalize, that's negative radical 3 over 3. And then to find the reciprocals, I can just go ahead and flip the numerator and denominator. So here we get 2 over 1, which is just 2. Here we have secant of 5 pi over 6. That's going to be negative 2 over rad 3. Rationalized, negative 2 rad 3 over 3. And then for cotangent of 5 pi over 6, we should go ahead and look to this version here, negative 1 over rad 3, because when I flip it, I'm just going to get negative radical 3. I don't want to flip this last one because it's going to put a radical in the denominator that I'd have to go through the trouble of getting rid of it. So now I have the exact values of all 6 trig functions because we had the x and the y value from the corresponding coordinate point at the angle 5 pi over 6. And I want to just take a second to notice how the reference angle here is pi over 6. That's how far I am away from the x-axis. And if I look over here to pi over 6, I have the same x and y value, radical 3 over 2, 1/2. The only difference is the sign, right? So negative is with the x value because I'm in quadrant 2. In this example, let's go ahead and evaluate the following using the unit circle. Leave your answers exact and simplified. So sine of 2 pi over 3. If we have the unit circle, then we can simply find the angle 2 pi over 3, which is in quadrant 2. And sine means we want the y value at that angle. So the answer here is going to be positive radical 3 over 2. Now let's go ahead and move on to tangent of 135 degrees. Well, 135 degrees also happens to be in quadrant 2. And we are looking for tangent, which is the y value over the x value. So here I'm kind of showing more work than I need to, because this could be done pretty quickly in our head, but just to show that it's the y value over the x value, it's radical 2 over 2 over negative radical 2 over 2. So the same value over the same value will cancel, and I end up with just negative 1. Now let's go ahead and do cosine of negative pi over 3. Well, negative pi over 3 isn't explicitly on the unit circle, as in I can't see it as one of these angles, but I can figure out which angle is coterminal to negative pi over 3. If I go in a clockwise direction, pi over 3, that's coterminal to 5 pi over 3. So that means that I'm looking for the x value there at 5 pi over 3, which is 1/2. So cosine of negative pi over 3 is 1/2. And then sine of pi, I want to go to the angle pi, which is on the left side of the x-axis, and the coordinate point there is negative 1, 0. Sine means I want the y value, so sine of pi is equal to 0. So if I have the unit circle, then I can simply choose the x value, the y value, or y over x, depending on which trig function I'm evaluating. If it's not exactly one of the angles that I see, but it is coterminal to one of the angles, I would just have to figure out which angle is coterminal to it to find the correct value. Now let's look at this example. We want to evaluate the following by sketching the appropriate special right triangle. Leave your answers exact and simplified. So we are now assuming that we aren't going to be given the unit circle. We're going to go ahead and look at this method for evaluating a trig function at an angle like 135 degrees. So let's try part A here, sine of 135 degrees. And here are the steps for using this process. So first we want to go ahead and sketch the angle theta. So sketch 135 degrees. That's in quadrant 2. So I'm going to go ahead and sketch 135 degrees, which lands me over here in quadrant 2. And the next step is to draw a reference triangle using theta prime, which is the reference angle, and properly label the side lengths with correct values and signs. So the reference angle here, the acute angle that gets me to the x-axis, is going to be 45 degrees. Now, if I'm on the unit circle, the only possible reference angles are 30 degrees, 45 degrees, or 60 degrees. So here we have 45 degrees, that's my reference angle, and what I want to do is construct a reference triangle. And that's just going to be basically dropping a perpendicular straight down to the x-axis from the terminal side of this angle. So I'm going to just drop a perpendicular straight down. That creates my right angle. Now I have a 45, 45, 90 right triangle. And what I can go ahead and do is use those special right triangle values for the side lengths. The easiest thing to do would be to use the original ones. So if I have a 45, 45, 90, then the two legs have a length of 1, and the hypotenuse has a length of the square root of 2. The only difference is that now we're talking about being in quadrant 2, and that's going to affect the signs, S-I-G-N-S, of the side lengths potentially. So here, if I go to the left on the x-axis, that means that this value is going to be negative. But if I go up on the y-axis, then this value stays positive. So I do have to label my reference triangle with my known values, but I have to attach the correct signs to them as well. And the hypotenuse is always going to be positive. So now, sine of 135 degrees can be found by doing part 3, apply SOHCAHTOA, to find the correct ratio of side lengths. So using this reference triangle, I'm going to go ahead and do opposite over hypotenuse. So we're going to have 1 over the square root of 2, which if we rationalize is going to give me the square root of 2 over 2. One last thing before we move on is just to go ahead and make sure we understand that it's okay that we use the original special right triangles even though the hypotenuse is radical 2 and not 1, because remember that the ratios of the side lengths are going to stay the same whether we scale up or scale down this special right triangle. In part B, we want to evaluate tangent of pi over 3. So we'll start by sketching the angle pi over 3. That's going to be over here in quadrant 1. So here's my angle pi over 3, which is 60 degrees, of course. And so the reference angle happens to be the original angle, right? 60 degrees is the reference angle here. And so if I drop myself straight down and create my right triangle, then opposite 60 degrees is radical 3. The adjacent side is 1. The hypotenuse is 2. Again, if we're going back to those original special right triangles. And the signs are going to both be positive. I'm going to the right and I'm going up. So I'm in quadrant 1 where everything's positive. So tangent is going to be opposite over adjacent. So radical 3 over 1, which is just radical 3. And this should be familiar because this is a quadrant 1 angle. This is how we found these values before. The only slight difference is now we're thinking about this in a quadrant. So in quadrant 1 of this unit circle. Now let's work on cosine of 330 degrees. Let's go ahead and sketch the angle. So 330 degrees is going to be in quadrant 4. So we're going to go all the way around to quadrant 4 here. Here's my 330 degree angle. That's my theta, but my reference angle is going to be 30 degrees. That's how I can get to the x-axis using an acute angle here. So we have our 30 degree angle. And so here's my reference triangle here. And opposite 30 degrees is going to be 1, and opposite 60 degrees is going to be radical 3. The hypotenuse is 2, but again, we have to be careful with the signs here. So radical 3 is positive, so I'm going to go to the right because I'm going to go to the right, but 1 is negative because I'm going to go down. So now my signs are correct, so now we go back and think, well, cosine is asking me for adjacent over hypotenuse, so radical 3 over 2. Now let's evaluate cosine of 5 pi over 4. So 5 pi over 4 is in quadrant 3. So we're going to go ahead and sketch 5 pi over 4 down in quadrant 3. And so the reference angle is going to be pi over 4. So that's how far away I am from the x-axis here. So that's pi over 4. Or if we need to go to degrees, 45 degrees to help us think about the 45, 45, 90 special right triangle. So I'll go ahead and drop my perpendicular to get my right triangle. And we know that the hypotenuse would be radical 2. And each of the legs would be 1. But again, we have to associate the correct signs. So I go to the left and down. Both of these are going to be negative, right? They're both going to be negative. So cosine of 5 pi over 4, cosine is adjacent. So adjacent to this reference angle is -1 over the hypotenuse is radical 2. We've done this so many times now, rationalizing this is negative rad 2 over 2. So we have to remember to associate the correct signs. I would say that's one of the most common mistakes when using this method. Let's go ahead and evaluate tangent squared of 7 pi over 4. Let's start by remembering that this is tangent of 7 pi over 4, all as a quantity squared. So we're really just evaluating the inside, tangent of 7 pi over 4. So let's go ahead and recall that 7 pi over 4 is in quadrant 4. So we'll go all the way around here to quadrant 4. We're going halfway through quadrant 4, making the reference angle pi over 4, which again is 45 degrees. So I'm going to go ahead and draw my 45, 45, 90. So the two legs are 1, and the hypotenuse is radical 2. Let's make sure and assign this leg a negative value because it goes down. And then let's see, tangent is going to be opposite over adjacent. So -1 over 1. So we have -1 over 1 squared, or -1 squared, which is just +1. In this example, we're asked to evaluate sine of 90 degrees plus sine of -240 degrees. So first let's remind ourselves that we have to do each one separately. Sometimes people think because they're the same trig function, they're both sine, we can do something like add their inputs together. That's not a property of trigonometric functions. I cannot do that. So I have to evaluate each piece separately here. Well, sine of 90 degrees is going to be handled in its own unique way because it's a quadrantal angle and we can't sketch a right triangle there. So we just have to remember, I will go ahead and just draw an XY plane here. We have to remember that 90 degrees up here corresponds to the coordinate point 0, 1. And sine is the y value. So sine of 90 degrees is 1. So that's the first part. Plus, now we have to evaluate sine of -240. So let's remember that negative means clockwise. So I'm going 240 degrees clockwise. So we're going to end up over here in quadrant 2. So I go -90, whoops, -90, -180, and I'm going an extra 60 degrees here to get myself to -240, because this is -180, again going in that clockwise direction. So this reference angle here is going to be positive 60 degrees, right? It's always a positive acute angle. So if I go ahead and drop this down to form my right angle, opposite 60 is radical 3, opposite 30 is 1, the hypotenuse is 2. Let's see, if I go to the left, that's going to give me a negative value here, and this is going up, so this stays positive. So sine is opposite over hypotenuse, so radical 3 over 2. So even though it was a negative angle, I still got a positive value out. So the angle the sign of the angle doesn't have anything to do with the sign of the answer, right? Whether it's positive or negative. It has to do with the trig function and which quadrant the angle lies in. So we have 1 plus radical 3 over 2. We can combine this together. If we create common denominators, 2 over 2 plus radical 3 over 2. So we get 2 plus radical 3 over 2. So these are not like radicals. We can't combine them together. So this is the best that we can do.